Hi, it's Moser with a quick tutorial on formula mass and molar mass. Molar mass is kind of revisited. We've talked about this before, but we're going to add a twist this time. So now that you know how to write chemical formulas, you can use those chemical formulas to figure out the average mass of a molecule or a formula unit. For instance, if we want to know the average mass of a single molecule of H2O, we know that the average mass of a single hydrogen atom is 1.01 AMUs. And remember that this accounts for isotopes that are out there that weigh more than 1 AMU. And the average mass of a single oxygen atom is 15.997 blah 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 blah. We round it to 2 decimal places to 16.00 AMUs. So it's a simple factor label. If we have 2 hydrogen atoms and one hydrogen atom has a mass of 1.01 AMUs, the total mass of hydrogen in a molecule of water is 2.02 AMUs. One oxygen atom, where every single oxygen atom has a mass of 16.0 AMUs, gives us a total mass of oxygen in a molecule of water at 16.00 AMUs. Add them together and you get 18.02 AMUs. Okay, let's do one more just to be sure we've got it. Okay, I've got our good friend iron 3 oxide, and you will need your periodic table for this. We're going to go ahead and just go to 2 significant figures. We're not building a rocket to Mars. We're not making drugs that people will take into their bodies. So we can go ahead and use 2 decimal places for significance. So that gives us iron. We have 2 iron ions, 2 iron atoms, and every one iron has a mass of 55.85 AMUs. We'll go ahead and do the math. So we have the mass of iron in a formula unit of iron 3 oxide coming in at 111.70 AMUs. And I have 3 oxygens. We said that every one oxygen has a mass of 16.00 AMUs. So those are coming in at 48.00 AMUs. Okay, when I add those up, I get a mass for every little unit of iron 3 oxide of 159.70 AMUs. Now I'm going to be careful with my sig figs. We're not governed by this because those are counting numbers, not measured numbers. So we have 4 sig figs to work with, so our final answer will be 159.7 AMUs. Okay, you can do this. It's not hard, and you'll start to build shortcuts as you go. Not a big deal. Now, let's talk about the compound that I just did. Is that a molecular compound? No, it's ionic. It's an iron oxide. It's iron 3 oxide. So let's talk about the difference in our language when we're talking about molecular versus ionic compounds. We say molecular mass when we're talking about the average mass of a molecule, but we can't really use that to refer to ionic compounds. Why? They don't have molecules! You knew that. So formula mass sort of stands in for molecular mass. It's the sum of all of the average atomic masses for the atoms represented in the formula unit for a substance. So when we do what might otherwise be the molecular mass for something like sodium chloride, we're really looking at formula mass because this is a formula unit. Same thing with that lovely iron 3 oxide we just did. We didn't find the molecular mass. We can't. What we found was formula mass. Now, that said, you will probably screw up occasionally and call it molecular mass when it's ionic. I do too. But you should be aware of the distinction so that you can at least mentally correct yourself and you aren't surprised if someone else corrects you. It's okay. We will make that mistake, but let's be aware of it. Okay, now, this is the exact same thing we just did. How many of each type of atom do you have? What is the mass per atom? Figure it out, add it up. Okay, got my answers for each individual one, added them all up, and I come up with 69.0 atomic mass units per unit of sodium nitrite. NO2, nitrite, not nitrate. Okay, very easy. You can do this. Super simple. Let's talk about a few where there's a bit of a trick. So when we look at calcium nitrate, CaNO3 2 times, pretty easy. Let's find the masses. I found the masses, and honestly this is how I usually set these up. The factor label's great for the bigger stoichiometry that we will do later, but this is a good shorthand. So that's times 1. Now, how many nitrogens do I have? Remember that the fact that the nitrate ion is in parentheses with a 2 outside it means I have 2 complete nitrate ions. So here's our visual. That means this is times 2. Now, how many oxygen atoms do I have? Well, in this case, I have NO3 in the parentheses and 2 outside. I have 1, 2, 3, 4, 5, 6 oxygen atoms. That's a really easy place to make a mistake, so be aware of that one so that you can avoid making that particular mistake. Okay, so I have the atomic mass for each element times the number of times that that element appears in the compound. Now I'm going to add them all up. I get 164.10 AMUs in that compound. Okay? The same thing applies with the other ones that I've chosen here. You have to be very careful about how many times an atom actually appears. Let's go ahead and actually just do the aluminum sulfate, because that one's a pretty good tricky one. Again, I'm taking my shortcut of just listing my elements, and I'm going to put in their atomic masses. So again, I've done the sort of visual aid of drawing the sulfate ion. You are under no obligation to do that. But if you have any doubt about why we do multiply the 4 by the 3, I find that this is pretty helpful. We obviously have 12 oxygen atoms here. So we have 2 aluminum, we have 3 sulfurs, and we have a whopping 12 oxygen atoms. That is a whole lot of oxygen. Let's do our math. Whoa, aluminum sulfate is heavy. 342.17 AMUs in a formula unit. Now, of course, we only have 4 sig figs, so we would express that as 342.2 AMUs. Okay, practice! Then take a FIP quiz.